In this work, we design an FPGA overlay for CNN inference with fine-grained flexible parallelism. A CNN is predominantly form of convolution operation where a given input volume is convolved with a set of filters to generate an output volume. Accelerating CNN inferencing on FPGAs is an extremely crucial task to meet performance requirements of high-performance applications. In this work, we propose an FPGA overlay for CNNs that can accelerate different types of convolutions, as shown in this figure. An overlay accelerator is synthesized and flashed once on the FPGA, but is flexible enough to process a broad range of CNNs through soft reconfiguration. Unlike other overlay designs, our architecture supports fine-grained flexible parallelism. A specific layer of a CNN is broken into smaller computation batches, and each batch is reconfigured at runtime to operate with a different parallelism mix. The figure here shows the overall workflow of executing a CNN on our overlay. The host side code for CNN inference can be written using any of the available libraries such as TensorFlow, PyTorch, etc. In this work, we used TensorFlow Python to test our overlay. The host code communicates with the overlay running on the FPGA through a C++ based driver code. The host preprocesses each CNN layer to identify a suitable parallelism mix that satisfy a set of constraints. The constraints are set to minimize the stalls and maximize the data reuse for each input fetched from external memory. The host configures the overlay to compute a batch of output feature maps by sending a suitable set of control words. The overlay uses the control words for hardware software configuration. The overlay acknowledges the completion of the configuration phase to the host. At this point, the host tags the input feature maps and filter weights into a data stream. This data stream is communicated to the overlay through the host driver. The processed output feature maps from the overlay are transferred back to the host code via the driver. The output feature maps are stored in the host memory to be used as input to the subsequent layers. We now discuss the hardware architecture of our overlay. We use a single engine accelerator design for our overlay. A single processing pipeline computes all the layers of the network. The output volume rendered while processing a layer is streamed out to external memory and later loaded as input when computing the next layer. We compute convolutions in a streaming fashion where the input volume is streamed and the necessary filter coefficients are prefetched and stored in registers. The prefetch of filter coefficients overlap with computation to avoid stall cycles. Each input feature map of the input volume is surface convolved with the corresponding depth slice of the filters belonging to the current batch. This computation starts only after the corresponding depth slices of all the current batch filters are available on our FPGA registers. Then each input feature map is streamed in a row major way to the corresponding surface convolution with respect to each filter. Once minimum number of input pixels for carrying out the filter convolutions have accumulated in the input buffers, surface convolutions can be computed at a steady throughput. At any point, the accelerator stores a set of rows from an input slice and multiple partially rendered output volume slices. The line buffer of the input ensures that only a working set of rows from the input slice is required to sustain a fixed number of convolutions every cycle. Once the filter batch is done and all the filter depths are convolved with the corresponding input volume depths, the output slices stored in the buffers are drained out to external memory one at a time. This drainage of output corresponding to a filter batch is overlapped by executing parallel convolutions corresponding to the next batch of filters. To do this, a second set of buffers are used for accumulating the output of the next batch. Note that the input volume has to be streamed again at this point. This double buffering scheme ensures maximum compute to memory overlap during the processing of multiple filter batches. We evaluate our overlay to process AlexNet, VGG-16, YOLO, and MobileNet targeting two Xilinx FPGAs. From the results, we can note that with respect to the throughput metric on the Zinc XC7Z020 board, which is also called the Z board, we outperformed other works by almost a factor of 1.2 to 2.3x. Also, our accelerator achieves far better performance density by almost a factor of 2x to 5x, both with respect to the FPGA LUT and DSP utilization for the same Z board. This figure also shows for every CNN and FPGA pair on a per layer basis how the theoretical cycles compare with the execution cycles and the additional stall cycles. We can observe that on the Z board, except for MobileNet, the execution cycles are almost matching the theoretical minimum, and the extra overhead in the total cycles is accounted for by the stall cycles. For future work, we plan to extend our synthesis framework to include emerging convolution layer types such as grouped and shuffled grouped convolutions. Thank you.